perspectives. Please.
Okay, thank you very much. Thank you very much to the organizers, and it's been a wonderful, wonderful conference, and really with a lot of excellent talks, making a lot of pressure. So luckily, this talk has already been solved by Greg, because he told me that the solution is very easy. The answer to this question I put here is money. So that's it. We can go home. Okay, so I'm gonna talk mostly about future instrumental aspects, but I thought I'd just make a couple of remarks about parameter estimation, because it came up a bit, and I think it is integral to having new instrumentation, to have the right tools to exploit it. And we have a long history when it comes to parameter estimation. And the interesting thing is that what we trust the most today is stellar masses, probably, and that's the last in the sequence. The various vertical things are various historical events that I'm not going to bore you with. Star formation rates, well, since the 1960s or so, people have calculated star formation rates, increasingly less confident about them as time goes on. And nebular abundances as well. That goes back really far back, because the history started really with start of atomic physics. But when we come to physical parameter estimation of SED fitting, we also have a long history where things have improved slightly. There's been a lot of emphasis on techniques in recent years. Even though the results when it comes to inferring star formation histories are still rather comparable, to Beatrice Tinsley's 1968 papers and what we get with the fanciest Bayesian techniques. The main difference is that we know what the uncertainties are, within twiddle something. But SED fitting codes kind of agree well. But I want to emphasize that they all use the same input, pretty much. So back 15 years ago, I gave a review talk on stellar populations, and I thought it was useful to sort of revisit this. So these were the main things I highlighted as things we should improve on in the coming years. And I wanted to particularly touch on the first one, which is model uncertainties. When we calculate a chi-square, or we write a likelihood function or whatever, we put in an uncertainty. That uncertainty that we put in is the observational uncertainty. That makes sense if your signal to noise is 5. Right? But when your signal to noise is 20, 30, 40, which is what we aim to because we want this beautiful data, then the uncertainties on your models are probably bigger than your data. And we don't have a good way to quantifying that. And we have talked about it for 20 years and we still don't have it. Right? And this is a major concern when it comes to exploiting high signal to noise data. The other bits, things have improved. TPA-GB stars, I don't think we'll ever fully understand them, but things have improved. I'm not going to talk about the IMF or the first stars. What I wanted to finish on, the only thing I want to really say a few words about is that another thing that's, is it the right word, fashionable? But actually very, very important. So if you go back 20 years, binaries, talks on binaries on stellar populations were dominated by people that liked to explain how complicated it was, and basically their parameter space, all the models filled the entire parameter space, so your degeneracies was 100%. And that really improved a lot with Jan Eldridge and Elizabeth Stanway's BPAS code, where they actually came up with a practical way of including binaries in their models, and they are actually extremely useful, but there's only one. And when people have started developing new models here, and that is happening, people are now having new stellar population models. The Kroc, for instance, the paper out this year, they find slightly different results from the binaries. So this continues to be a big uncertainty. The cross-check on this, which is what I really was hoping for, back then, we were hoping that you could avoid binaries. I think we cannot do that. 70% of all young stars are in binaries, so we can't ignore it. And I think it's very important that we get it right, and that needs time. So my comment here was really to say that I think we spent a lot of time improving software, and they are very fancy, but if your ingredients are not the right thing, That's like going to the kitchen and buy the finest frying pan and then buy half-rotten tomatoes, right? It's not going to be good food. So you have to be, now, current models are much better than half-rotten tomatoes, but you have to do as good as you can on the ingredients. And I think that's an effort that we have to make. Now, running away from this question, which is hard, I'm going to go to something a bit more easier, which is to dream. And we're going to look at the future instrumentation scene, right? So we're going to go 10 years into the future. We're going to jump into our DeLorean and zoom, we're going to put our hair back. And so this is what we're going to have. Right? It's very European-centered. We're going to have the ELT. We're going to have Mikado, Morpheo, Metis, hopefully Harmony in 10 years' time. It's going to be a fantastic machine, but it's going to be only one on the darn planet. Hopefully there will be a US ELT nearing completion by then, but you know, this is still going to be a very hard facility to get time on, and it's going to be particularly good for individual sources. VLT is going to be crucial. We're going to have exciting new instrumentation, cubes, Mavis, and Blue Muse, particularly Blue Muse, I would say particularly for this conference is going to be very interesting, complementing Muse with a blue end and getting access to a lot of interesting stellar and nebular diagnostics. We're going to have Rubin, we're going to have 10 years of LSST. We're going to have plenty of time from years of going on with the SKA precursors. SKA phase 1 is going to be done, which I put up there because nobody knows what phase 1 means, so it's easy to say that we will have it done. But it will be something pretty amazing. JWST, we'll have 10 years of JWST by then, and hopefully another 10 to go. We will have Euclid data releases, we'll have a whole lot. This is the context in which we should dream, right? I have another slide which you can look at your leisure. And so the lesson here, to some extent, what I would take away from it is that we're going to have, the coming 10 years is going to provide us with a fantastic legacy of wide field imaging surveys, multi-band imaging surveys. And now we need to exploit that because that on its own, imaging is fantastic. It gives you so much intuition, gives us so much starting point, but to really understand the physics, you need to move beyond that. And, but I thought since we had a data release last week, I thought I'd give you a few slides on Euclid because I'm quite heavily involved in Euclid, as many of you are too. And so this is going to give us 15,000 square degrees of high resolution optical imaging and near infrared imaging. And the reason why we can do that with Euclid compared to something like HST is these fields of views where you compare the Euclid field of views of the visible and the near infrared is pretty much the same. On the left, Roman, and then JWST and HST you can see up there. And if you take into account the slew times of HST, you can estimate how long it would take HST to do the image that's in the background, which is a Euclid image. And it's a factor of 1,000, right? So if you want to do that 15,000 square degrees, you're not going to choose HST or JWST because you won't ever finish. Okay, so maybe let you know, when, those of you not in the consortium, when are you going to get it? So we had 12 square degrees released last week, so that you can get already. I'll put the link in. The link is in the slides. I'll show you some results from that. Next year in March we will have 50 square degrees as a normal survey. You will get visible imagery, near infrared images, 1D spectra, etc. The big jump is going to be in 2026 when you'll get 2,500 square degrees. Then there will be another release with 7,500 square degrees in 2028, and then the full 15,000 in 2031. So now that we're flying and actually observing the uncertainty on these times, it's not that large anymore. So what did we do last week? Well, we released the Euclid early release observations, 17 sources, global clusters, star-forming regions, galaxy clusters, galaxy groups, galaxies individually. That's a link to actually get the data. There's some examples. We have a lensing cluster of L2390, M78, which I had to correct 10 times when writing these slides because I typed M87 every single time, which is a slightly different object, and a Milky Way analog. One thing that you won't have heard so much about Euclid, but which I think is quite striking, is if I zoom in on the lensing cluster, here's a version of that where the intracluster light detected from the Euclid data is overlaid. So Euclid is actually going to be very good at seeing this low surface brightness. This is going to, in a single standard wide field, 15,000 square degrees, we expect to go to about 30th magnitude per square arc second in a 10 arc second square. So that's something that I think is going to be quite fun. And one thing, if you want to play with these images, which I encourage you to do, one thing you will notice is that this doesn't look much more impressive than an amateur astronomer's photo of the same galaxy. But if you zoom in, it resolves. Oh, interesting. Yeah. Ha-ha. Okay, I'm not going to run it again because you can just believe me, it resolved into stars. So, yeah, so you can play around with the data. The papers are all online. It's a lot of, I hope we will find referees for all of them. Some of the nice results that we have, this is just a random collection almost. It's a mass function in Perseus. There's a single exposure in Perseus, just one shot, 200,000 galaxies detected, going down to 10 to the 7 or so in solar masses. In the middle you can see the dwarf galaxies detected. There's about 1,100 dwarf galaxies detected in the cluster in this single shot. And maybe you can, I don't think so. There's some squares in here that are slightly darker than the others. I don't think you can see it, but you can see it in the paper. Those are the HST pointings in Perseus. And you can see that the richness of the dwarfs is all over the place. And you find these really funky random versions that have multiple cores. These are dwarf galaxies, very faint dwarf galaxies with multiple cores. So those are going to be fun to understand fully. And the thing is that we get samples of these with such a big area. Thought that they might have to do with mergers, dwarf-dwarf mergers. And on the right you can see another thing that I think Euclid is going to be awesome for. It's not going to be awesome for the faintest galaxies, but it's going to be awesome at finding the brightest of the high redshift galaxies. Right? So this is Lyman break galaxy search in the Abell 2390 field. It's about 26 Lyman break galaxies at redshift greater than 6 that we find in there. And then in the same field, this is an image of 2390, but there is these random other clusters with lensing signal in the same field, in the same image. There's going to be a lot of lenses. That's going to be fun. But it's not just imaging that we're going to have in 10 years. We're going to have all this Euclid stuff, so I'm not going to talk more about it. Now, we're also going to get a lot of radio. Right? This is also going to be transformative for many of us. And I think you have to take both of these things into account. And so now I'm talking optical, near-infrared, radio. So there's a gap, right? So I'll come back to that. So what's my very biased view take on this is that there's been a lot of subtle trends that I've seen throughout the meeting. And to better characterize subtle trends is you need large samples. You want the rare sources because they can be very informative. We had that in several discussions. That means you need large volumes. Many of these imaging surveys will give you candidates, but you need to follow them up. Systematic uncertainties is something we tend not to talk so loud about, but they are of course crucial. And one thing that you all have been emphasizing is the complex interplays that you see in all the science you're doing. And to understand complex interplays, you very often have to condition your samples on various parameters. As soon as you condition and split samples conditioned on multiple parameters, the number of objects you need increases, as we know, exponentially. So I'm not going to talk about the last thing. If you want to learn about machine learning in astronomy, I recommend Hogg's recent AstroPH paper. I think it needs some thinking indeed. So, how do you want to do that? Okay, so the two things I'm going to touch on, this very random pick because I'm not going to stand here talking until it's dark. I'm going to talk about arguing that we need more spectroscopy, optical near-infrared spectroscopy, both fibers and integral field spectroscopy, and also argue that what you also need is more sub-millimeter data, because that's a gap, right? We are going to have optical near-infrared surveys, we're going to have radio surveys, but we're not really getting sub-millimeter surveys at the same level. Of course, you need a whole bunch of other things, but I'd really love to see a far-infrared space telescope that's up more than 3 years, but that's not on my watch, I think. Okay, so that's where we are. So sub-millimeter is an area where we haven't had a lot of survey facilities, and I think it is something that some people in the community very strongly feel we should have. The Fred Young sub-millimeter telescope will be a go at that, but it's a 6-meter dish, so you're going to be limited by confusion. PFS is going to be fantastic for optical and near-infrared spectroscopy, but it's not on a dedicated telescope, so you're going to be subject to the whims of the TAC. Formos and Weave is on survey telescopes, but you're going to be limited by the fact that your telescope is 4 meter. Right? And in the near-infrared, moons will be excellent, I hope, and MOSFIRE has already shown that. So I'm going to talk about 2 possibilities for the future, because now is the time to think about what we want to have in 10, 15 years, right? These big projects take 10, 15, 20 years to realize. So now, if you want to have something in 2040, you better think about it and realize it now, right? So that's what I'm going to talk about. These are 2 efforts to try to basically present or projects that maybe ESO will be convinced to take on as their next project. I'm strongly involved with WST, but I think for this conference I also wanted to present at last, which I'm not involved in. And so you can say, oh, they are competitions, but I'm going to try to be fair about both of them. And I got a lot of help from Claudia Ciccone, who's the PI of At Last, to provide me with some slides, and some of you might also be involved, so you can help out if there are questions. So I'll start with At Last. So this is a project, this is a proposal to build a 50-meter diameter sub-millimeter dish with a wide field of view, right? 2 square degrees, a rich instrumentation set, both I will show you them in a second, and covering quite a wide range in wavelengths, okay? So 350 to 10 millimeters, and that's, you know, if they can build that and they can get the atmospheric conditions to actually observe, that would be fantastic. And the argument here really is that you need a single dish together with an interferometer, right? We have ALMA. ALMA is amazing, but it's not the best survey machine if you want to cover square degrees. But it is fantastic for following up. And the single dish cannot compete with that, but it complements each other very, very beautifully. So you can use the single dish is what you want for large areas, is what you want to find sources, what you want to use to really improve and make sure that you can exploit ALMA the best possible way. And so At Last has really, its main selling point is a very large primary mirrors diameter combined with a large field of view. So LMT has a similar diameter, but the field of view is small, right? So what you want is that combination, and that's of course not trivial. But it would mean that At Last would be a fantastic survey facility. And just to illustrate the advantage of the big dish, here's just a comparison of a simulated observation from ACT and At Last, and you're just limited by confusion noise with a small telescope like 6 meter. So the instrumentation they are considering for At Last is a combination of cameras, well, effectively calling them cameras, and IFUs. I'm not going to go through all the details, but one of the things that I would emphasize is that the bandwidth that they are considering is quite interesting. Right? So that's particularly interesting for the local universe where you have lots of lines in the same field. So to illustrate, here's a couple of examples from their science papers. This is an illustration of the cold CGM, which is something that has come up multiple times in the meeting, whether there is a significant cold CGM. It's hard to detect because it's diffuse, it's hard to detect with interferometer. And here you can see from a simulation, in the middle it's the simulated ALMA observations and the simulated At Last observations, both 10 hours exposure. The details of the simulations you can find in this Lee et al. Paper. They also want to do, by the wide wavelength range, they're wanting to do very big surveys. So, thanks. So at 1,000 square degrees continuum survey, a 1 square degree line survey really covering a very wide range of lines. And you can map the LMC and SMC really efficiently, doing a very nice CO map of those. So that's the sub-millimeter side of things. As I said, I'm heavily involved in the WST project. What we're sort of pitching is that what you really need is optical spectroscopy on a massive scale, right? So what we're considering is a telescope, dedicated telescope, 12-meter diameter, field of view of 3 square degrees. And what we want to do is we want to have both a low resolution and high resolution multi-object spectrograph with a lot of fibers and an integral field spectrograph. And for some reason, my edit here hasn't taken. That should say 3 by 3 arc minutes. I'm not that crazy. Sorry. Here it's correct, at least. Right, so what we're envisaging is 20,000 fibers, right, in this patrol field. And then in the middle, you have an IFU that you can move independently of the fibers. So you can do a mosaic of 3 by 3 fields with this. And that puts us in a completely different regime to most other facilities. This is a field of view of the WST integral field unit compared to everything else on the market. The size is very similar to the Mauna Kea spectroscopic explorer, but that of course has the problem is the 2 first words in the name. So what we want to do with it, well, I think it follows very much what we've heard of in the last couple of days, which is to trace the large-scale structure, to trace the cosmic web on a much more densely than we have previously been able to do, to really, really nail down, get massive spectroscopic surveys. We're thinking about reaching a redshift 2 to actually use Lyman alpha tomography to probe the cosmic web with about 1 million galaxies per cubic megaparsec in a delta Z of 0.5. So right, that's what we are sort of ballpark aiming for. So that would allow us to do studies of the cosmic web on a scale we haven't possibly been able to do before. But at the same time, you can also do these massive surveys with the IFS. And that really you want to push down to study the galaxies on scales smaller than 100 parsec. Fangs has really showed us that is a very powerful way of understanding the matter cycle inside galaxies. And with such a large IFS, you can start building up samples comparable to Manga and Khalifa with resolution better than 100 parsec for about 1,000 galaxies or so. So that's something we think is very powerful. And at the same time, you can use the fibers to observe all the large-scale structure around these galaxies. Right? So that synergy between the IFS and the fibers is something that we don't have anywhere at the moment, and it really requires us to think carefully about how to approach it. And there are many more ways of doing that. So we want to push also for the lower redshifts, so redshift 1-ish out to redshift 1, again recovering the cosmic web, but very densely, and now use the IFS in the center to trace the small-scale structure of the cosmic web and the near surroundings of the galaxies in that redshift range. This is a simulated observation from Clotilde using disperse, which, as we have heard, it's kind of the tool of choice. And we can also do this, and this is something that Muse has shown is possible, is to study the CGM in emission. I'm not going to get into the discussion of whether you can do the filaments in emission, because that is more of an issue. But the CGM you can detect in emission. At high redshift you can do it with Lyman alpha. And at low redshift in some sets of galaxies you can do it in magnesium 2. Again, a resonant line. It provides a different view of the feedback processes that happen in these galaxies. Currently, this is completely limited by sample size. You need a much larger survey to really get these ones going. But we're sort of aiming for this thing to allow us to do 80, 100-hour integrations with the IFS while doing a dense spectroscopic survey with the fibers, moving the fibers around outside of that. So I'm going to leave you up here with some conclusions. I think we really now is when you have to start planning what you want in 15 years' time. So that's my message. But I also presented two, I think, very interesting projects for this. I mean, I have my own personal scientific interests, but I think both of these are very valuable scientific ideas for the community as a whole. And there's, of course, much more science in here than I talked about. So I'm also leaving you with a bunch of links that you can go to I've uploaded the talk, so you should be able to download it there. That gets you to the various web pages and the various white papers, etc., that describes these projects. So I'm going to leave you there, and thanks.
Questions for Jarle?
Jarle, thanks a lot. That was nice. So at the moment, both Atlas and WST are dreams. And so the question for you is it ESO the only hope? And how the community can help in making both of them become a reality?
Right. I didn't include it here. Okay, so that's a very good question. So first of all, ESO will open up a call at some point, or at least make a process for choosing what's their next big project after ELT. So something that the community dreams about will happen. Whether that's these two projects or not, I think we will have to fight one corner for. But yes, so there is, of course, so there is an effort on the Atlas side, for instance, to work with the Japanese LST project, and they have joined forces. Claudia informed me. So there is I think some of these big projects naturally are transnational, and they were both aiming to go to Chaknantor Plateau because. So it made sense that they joined forces, and I think that's one of the ways that we can do it. I think, I would have liked to see more international collaborations on these very big projects, but hopefully it will happen.
Yeah, second Luca's comment about nice overview. To begin with a comment and then a question very much in the similar vein. I think in terms of dreams, we can't forget the third dream of the Alma community, which is a second generation Alma, right? So there will be at least three. And unfortunately, that means the millimeter community will at some level divide. And I've seen this firsthand. So the question is, you can debate the costs of these, but the three, including the third one, it has to be in the neighborhood of 500 million to €1 billion each. So we're talking really not quite ELT, but comparable to anything else ESO has done, including Alma, the European share of Alma, but more. If you look at all these missions, we love galaxies. We're a loaded crowd here. Most of those missions you're looking at were partly sold on galaxies, but they were also largely sold on cosmology, dark energy, dark matter, or exoplanets. And there will be little bits in those three dreams. Do you think there's the political backing of the whole community that they could invest that kind of money in one or more things, where the galaxy evolution, information science would be the prime driver?
Okay, so that's so that hits on multiple levels. So let me take a step first, address just your comment, which is a very pertinent comment. I think it's not just Alma version 2. I think if you look at what's VLT unique for, we tend to forget it in our community, but I would say the real uniqueness of VLT arguably is the VLTI. Which addresses a very smallish part of the community, but there's no competition on the planet for that. So I think that's another area where there's likely to be some community pressure. I think the other place where I would say, and I was on one of the slides here, but I didn't talk about it, where I think there is a lot of pressure is from the gravitational wave community. And that section, I mean, the Einstein telescope will come at some point. It's going to be crucial that we can address the needs for that community. How that's going to be done, I don't know, but so there's going to be multiple interests in this thing. And I think both Atlas doesn't have a very strong cosmology case in my personal biased opinion, but they have a very strong galactic nearby case. Both of these two, both WST and Atlas has a very strong transient component, which is another area where I think you want to optimize operations in a way that you can really make use of all the transients we're going to get from LSST. So I think there is a broad component to both, and I think both collaborations realize that it really needs to go from solar system to cosmology, otherwise they are basically dead in water. But I'm not going to, I don't know what process will be followed by ESO on choosing this, but clearly it is important, and it was stressed that it was very important that the community came on board for instance, WST, and that's why we had a wide call, and we have like 400 members of the collaboration now, spanning from solar system to cosmology, but it is essential to have that span. I completely agree.
Yeah, thank you, Jarle. Thank you again. I think we need to move on. Sorry. And we have the conference summary by Antonino Marasco.
Yes, okay, it works. Okay, hello everybody, thank you for staying here till the very end, and for those of you who left, I mean, I cannot blame you, I understand. So I'm gonna provide, I've been given the honor and the burden to provide you a summary of this amazing conference. I don't have to explain to you why this is an honor, because it truly is. And the burden part comes from the fact that I don't know you, but in my experience at conferences, it's very easy to provide a very bad summary. Okay, so I'm not sure whether or not I'm gonna join the proud tradition of bad summaries, but even in that case, it's gonna be an honor. Okay, so let me begin with this one slide to rule them all. So before basically coming to the conference, I went through all the abstracts that have been submitted, and I tried to classify into 5 broad categories, which I believe are the main thematic categories that we've been discussed during these 5 days. So we've seen studies about gas accretion onto galaxies, divided in between a direct evidence, or better, the lack of the direct evidence from H1 studies, and indirect evidence from integrated galaxy properties. We have discussed star formation physics, both in terms of molecular cloud physics, turbulent, formation of stellar clumps at various Z, and also in general about the stellar mass assembly, how it proceeds during time. And of course, the topic of star formation physics is very much linked to the topic of stellar feedback. I put together also the AGN feedback. We didn't discuss that too much. And this has been discussed and proposed in terms of how this impacts star formation, but also in terms of how we can characterize outflow properties at various Z. We had not so many, but important talks about metallicity, both as a tool to trace the galaxy assembly history, but also about the techniques. How do we measure metallicity? And finally, there was a big session on the environment that just ended up today, and we discussed not only the classical physical processes, but also more large-scale processes like how filaments affect galaxy formation physics and the formation of protocluster and so on and so forth. So I'm afraid that this is going to be the only unbiased slide, okay, where all your names are in them. I actually took the liberty to name you either in red or in blue, depending on whether or not the study that you presented was more theoretical or observational, but do not feel offended if I put you in the wrong category. I mean, I enjoyed all the talk. So for the rest of this talk, I'm going to focus on each of one of these 5 aspects, and try to present a bit what I feel that personally are the highlights, or what at least I find the most interesting thing. So this has to have a very personal imprint in it, because I'm an astronomer, so interested in a subset of the things that have been discussed, so I can only present a subset of things that have been discussed. I'm going to use traffic light, okay, for the rest of this talk, where when I use the red, I believe, so these are all personal opinion, that there is a substantial tension between different studies or in between the comparison between theory and observation, okay? So there is something must be done to improve. We should all sit together and try to assess where the problem is. Now the green light is that, well, there are different studies that are converged, or at least they are providing, for what I understand, a more robust understanding of what's going on a given topic. And the yellow light is whether it may be that the studies are a bit unclear and conclusive, well, mostly because they have been presented new methods that require maybe further investigation. So if you want to oversimplify this scheme, basically red, we agree to disagree, we agree, or I have, maybe it's me, and I have no idea what's going on. So let's start with the first topic, which is gas accretion onto galaxies, which is something that, you know, it's one of my favorite topics. Let me start with Mongoose, that has been discussed and presented by Erwin de Block. This is a beautiful collection of deep H1 observation of nearby galaxies. The depth is such that we easily reach column density of 10 to the 18 atoms per centimeter square, or even below that. And one of the main goals of the Mongoose is to go so deep that we can really find evidence for direct gas accretion onto galaxies in the cold neutral phase. Mongoose data are still being collected. We still have to analyze them, so I'm not going to discuss the details of what the observations are telling us, but what Erwin showed is the comparison with mock H1 observation from hydrodynamical simulation like TNG50 and FIRE2. Not all the galaxies, but maybe of the galaxies, oh, maybe I should use this pointer. Many of the galaxies in the simulation, they look like this, so you can see that there is clearly a disk, but around the disk there is a lot of low column density stuff that is a bit irregular. There are these little clumps and little filaments that we do not really see in the data. Even if you look very deep, you can see actually clumps in the data, but every time you see a clump, there is typically a stellar association. So it's basically a dwarf galaxy associated to it. And this is not the case. Erwin showed that you can be a bit more quantitative, but look at the distribution of the H1 column density or the velocity dispersion, and there are substantial difference, quantitative difference between the two. These differences are caused, as Erwin discussed, not only about the feedback that is implemented in the simulation, but the actual mode of gas accretion. These filaments are impacting the galaxies and are changing the column density and the velocity distribution function in a way that it doesn't look like in the observation we see. So the question is whether or not we believe that there is a tension between the models and the data in the mode by which present-day galaxies are acquiring their gas. I believe, personally, that the answer to this question is yes. This is a talk presented by Nir Mandelker, describing the physics of filaments of cold stream that accrete onto galaxies as a function of the redshift. And what I get from the talk, and actually also talking to Nir himself, is that we have an overall good understanding of the physics of these filaments and what are the most important ingredients regulating the physics of this filament. But then the devil is in the details, because when this filament enters the circumgalactic medium of galaxies, you have a combination of physical effects, like Kelvin-Helmholtz instability, radiative cooling, the entraining of the CGM, so this mixing layer, self-gravity, magnetic field that you should take into account, and this also involves knowing exactly the turbulence properties of the CGM that are not known either observationally or very much theoretically. And the consequence of this is that you cannot really in great detail predict what is going to be the fate of these streams, because you are building up many ingredients of physics and you keep piling up and things start to change. So when the streams enter and breaks down, you can imagine that there is a collection of clouds that have to survive somewhat in the harsh environment of the CGM. And this is a talk this is part of the talk presented by Andrea Fruni that shows that the fate of little clouds that are in the circumgalactic medium, you cannot really predict it a priori, no, in real detail. It depends, for instance, on the resolution. You change the resolution, you change the surviving time of these clouds. And a consequence of this is that you cannot know very precisely when and how this cloud will impact the disk. Right. So I believe that because of all this, we have not pinpointed yet the exact modes by which extragalactic accretion onto galaxy take place. So to me, this is a red light, and you can have a different opinion, but this is what I truly believe. On the other hand, gas accretion onto galaxies can be inferred in a different way, like in an indirect way. So this is a talk of Artemikam Sfarigna that basically inferred, well, basically you have your beautiful observation with the IFU, integral field unit, of a galaxy. You can infer the star formation history if you believe in the models that are allowed you to extract the star formation history. We Yarle dedicated a slide, an entire slide, trying to, the message is that you have to be careful, but assume that you can do it. Assume that you can know the metallicity of the galaxy from the star formation history that you get. You use a closed box model, and you realize that there is a discrepancy between these two, and the discrepancy can only be accounted for if you account for an inflow component, of which you can model. Okay? And so this method that is relatively simple and is not particularly new actually allows you to reconstruct the star formation history of galaxy and give results that they match at least with the idea of how things in my head are supposed to work in the universe. Okay, you get a flat accretion history for normal spiral galaxies, and at a fixed mass of your galaxy, the accretion history changes depending a bit on the morphology of your galaxy. Okay, so green light for me, meaning that this is an approach that should be pursued together with measuring direct evidence for infall, but we need to be careful because there are many open questions here. So how much do we trust model non-parametric star formation history, or in general star formation history of galaxy? This kind of accretion model bypasses mergers or traumatic events that can occur in your galaxies, and I will touch this point later as well. And of course, the elephant in the room, the role of IMF in regulating the metal content, and so on. But this is something interesting. So let's move to topic number 2, star formation physics. I'm going to touch only a few things here. So both Robert Kennicott and Levi Lin show, this is actually a plot made by Levi Lin, show this beautiful three-dimensional correlation between surface density property, so surface density of star, surface density of star formation, and surface density of molecular gas, showing this beautiful three-dimensional relation. Basically on this plane, what you have is the so-called resolver star formation main sequence, and she found that basically this is the most scattered one. And when you see many correlation, you identify the one that is the most scattered one, it makes perfectly sense to believe that this is a derived property, no? So this study suggests that the spatially resolved main sequence is a byproduct of the Schmidt-Kennicott relation and the molecular gas main sequence. Okay, so and the physical interpretation is straightforward, and it makes sense that the star formation depends on the molecular gas surface density, and this is set by the gravitational potential provided by the star. And I was wondering whether there is actually a very nice connection with what people call this is the volumetric star formation law. This is a two-dimensional relation between the gas volumetric density and the star formation rate volumetric density. And these two things talk to each other because in order to compute volumetric density, you need to account for the flaring that comes from the gravitational potential provided by the stellar component. Okay, so there is basically the stellar surface density to some extent included into this. And so one of the question that I have is whether or not these two relations that both look quite fundamental to me, they are actually the same, they talk to each other, or maybe they tell different things about how star formation proceeds in galaxies. And I leave the authors of this work and people that are more involved into this topic than me to discuss that. Stellar clumps. We had several talks here. I'm only highlighting what Angela Adamo and Miroslava Destojes-Zavasky said about stellar clumps and giant molecular clump formation at high Z. I'm showing a green light here because I have the impression that we are learning, now we know much more about gas fragmentation and how these stellar clumps are forming in the high redshift universe. So we know that they have an in situ origin, and this comes from many different observations. No? When you see Hadron Galaxy, the scale height of this clump is compatible with that of the disk. The clumps are co-rotating with the disk, and if you model the redshift evolution, it's basically inconsistent with emerging history. So they must have an in situ origin. And so the in situ origin, the idea is that gas is fragmenting due to gravitational instability. And then there are other observational evidence that are perfectly, are interesting, but I'm not going to comment too much on that. When you move to low redshift, we have seen the talk of Eric Junke showing, discussing the properties of clumps in the tail of jellyfish galaxies. Okay? These beautiful images you cannot really see here, but basically there are many of those. And I was wondering whether or not these HST clumps in the jellyfish galaxies, local jellyfish galaxies, could be somewhat, a counterpart, a local counterpart of what we see at high redshift. They live in similar harsh environment condition. The mechanism of formation is probably different, but perhaps they can be used, as a laboratory to study what's going on at higher redshift. The open question that we have in both cases, both for these galaxies here and for the clumps at high redshift, is what is, I believe, the fate of the clump that has not been discussed very much. Especially those at high redshift. So what happened to these clumps? Do they become part of the bulge? Are they get destroyed by tidal forces and then distribute across the disk? It's not fully clear to me what happens. For these clumps instead, we start to have a feeling that they may become something, okay? And we have this beautiful talk by Enriqueta Iorice suggesting that maybe ultra-diffuse galaxies in cluster can have this kind of origin. And I believe that also Ariel showed in his poster something that points over this direction. I believe that this is particularly interesting. But how do clumps form in general? We need some theory here, so I wanted to highlight the talk of Carlo Nipoti that presented this 3D Tumbre instability criterion, okay? So the idea is that the Tumbre instability criterion is bidimensional, but you can account for the flaring of the disk in order to introduce basically the third dimension. And even if you pick a disk that is supposed to be unstable, when you look at it into 3D, you find a higher stable regime because you are unstable only very close to the disk, and perhaps you start to become stable in region outside of it. They basically applied this Tumbre instability criterion in a set of galaxies, trying to understand the role of the importance of this instability, finding that in fact at high redshift most of the galaxies show at least some region of instability leading to clump formation. Now this model here can even predict, although it's very simple, it's axisymmetric, can predict the mass size distribution of these clumps, and therefore one of the questions that I have is that whether or not these models are ideal to be applied to high redshift galaxies to compute the clump properties at various z, okay? Or maybe are too simplistic. I think that this is a simple, these are simple models that can be applied to many different observations to assess whether or not fragmentation leads to the properties that we see at high redshift in galaxies. Okay, let's move to stellar energy and feedback. So here, Sandro unfortunately is not here, and he showed, this first slide is not about outflows, it's more about how stellar feedback regulates the property of disk. Sandro highlighted the importance of self-regulation due to the balance of star formation and feedback to regulate the properties of the galaxy on very short time scale. This smooth oscillation around the main sequence galaxy caused by this kind of processes. And on top of this, there is a long time scale evolution due to the entire assembly processes and environment. Now, in one of the first slides, there was, I find it very strong sentence. There is a paradigm shift. Star formation of galaxies at early times is sustained over, I'm reading what actually is said, over a prolonged period by gas accretion instead of short bursts induced by mergers. So this is a very strong sentence to me, and I really wish that it is right, and I was wondering whether or not we all believe that this is true. Do we believe that the bathtub model, okay, linking dark matter, gas accretion, and outflow, is the main mode by which galaxies evolve in all environment at all redshift, or there is something more? Well, at low redshift, it seems that for most galaxies this is the case. This is a plot shown by Dan Fisher with dynamo galaxies, showing that the relation between the depletion time of the molecular gas versus the velocity dispersion, and this follows this sigma to -1 relation that is actually predicted by this feedback regulated model. So do we now believe that traumatic events like major mergers or even minor mergers have only a minor or negligible importance in setting the properties of galaxies at all Z? By looking at the abstract that you submitted, I found that the word mergers appear very, very rarely. So I have the feeling the community is going in this direction, okay? Which I like it very much. But in a universe where most galaxies live in groups, and I've always been told that the group environment favors merger because of the velocity dispersion is exactly the number that you need. I still think that perhaps we should meditate a bit about it, a bit more. Now we talk about winds, okay? We had more than one talk, but at least two highlights. One of Stefano Carniani showing the ionized gas outflows at high redshift with JWST. Beautiful, say, oxygen tree line showing a double component. The narrow one is supposed to be the disk. The broad one is supposed to be the outflow. You can do your magic and work numbers for the mass loading factor, obtaining values that are modest, not so large, of the order of unity, which makes sense. But we've also a talk about outflows in say more local galaxies, not so local, a redshift of 2 by Alice, who showed that if you actually have a model for a rotating disk and you apply it to the spectra that you have, in the end, what's left for the outflow component is very, very small, and your mass outflow rates become actually very small. So not any longer mass loading factor of a few, but mass loading factor of a few percent, which is actually consistent with some of the observation that we have in the local universe, but not all the observation that we have. In this plot, you can see that there is a big discrepancy between what some people measure, what other people measure, and what is predicted by hydrodynamical cosmological simulations. So there are like 4 orders of magnitude, okay? So I believe that this is a big red flag. So there was, yes, other talk by Erin Kadofong trying to find other numbers with different techniques. So, red light and a series of questions. The question can be really many. So, for instance, you can ask yourself whether or not the warm ionized phase is the dominant phase of the outflow. Or if you have galaxies that are outshined by the outflow component, they may well look like rotating disks. So are these things common in the universe? And you can ask yourself also what is the fate of the expelled gas, no? Because you can use the escape speed of your galaxy as an indicator to understand what is the effect of whether or not they are escaping the halo or not. But this is all indicative because you are bypassing the entire hydrodynamics and you don't actually know what's going on. Also, the mass loading factor in simulation are still very large compared to observation, but this may be an observational bias. So we need mock observation of the simulation to assess whether or not observationally we are seeing something different, and we cannot basically model the outflow and we come up with the wrong number. And finally, we should agree on whether or not the mass loading factors among different simulation suites are consistent with each other. Not only the large-scale simulation, but also when you go to smaller scale, the zoom-in simulation, simulation of individual galaxies, and very, very local simulation as in Tigress. Dylan Nelson showed beautiful result from illustrious TNG, where the outflow is basically, outflows are capable of emptying galaxies of their gaseous reservoir. So your the baryon fraction is very, very small around galaxies. You see these big blue blobs, and most of the baryons are actually much beyond the virial radii. And I believe this is a green light for me, as opposed to this red light here, because this gives testable prediction in various mass ranges. Now you can use X-rays, you can use absorption line, and so you can really go there and check whether this prediction is valid or not. And this is connected to the powerful of the outflows. Environment. Benedetta showed this plot that just suggests that even in local cluster galaxy, environment can be very, very complex, and you have a collection of very different environmental effects. She focused on the two that are the most important one. Starvation, that gives this slow process of quenching, and run pressure stripping, that gives this fast process of quenching. And well, the take-home message from this plot is that if you count the number of transition galaxies that are sampling this slow process of quenching, and post-starbursts that are sampling this fast process of quenching, the number is very much the same, but since the time scale are different, you infer that the run pressure stripping is the most important process in nearby galaxies, and nearby cluster galaxies, sorry. And I think that this is the main thing that we understand about environment evolution. We understand, I think, very well what happened to galaxies when they fall onto cluster right now. And this actually thanks to all the GASP team, but also other studies that have been done in the past. We can use simulation to study a bit more about jellyfish galaxies. So if you want to move from 100 to 9,000, it's an excellent idea to use TNG50. You find, for instance, a very important prediction that most jellyfish are found in groups, which can be tested if you have good observation. You have GASP 2.0 with an incredible volume and a lot of hours at Muse or another instrument, but it's good. From the simulation point of view, we had many talks, Stephanie Tonnesen, Nina Ackerman, trying to model wind tunnel simulation, and so to see what are the effects of run pressure stripping onto galaxies. And these are all effects that we actually see in observation. So the enhancement, yes, enhancement of the dense gas fraction, star formation enhancement in the central region, radial inflows promoted by run pressure, air flows in the central region promoted by torques. These are all effects that in order to understand, you really need to run hydrodynamical simulation of some quality, but they are consistent with what we observe, right? So this is the enhancement H2 fraction measured by Alessian run pressure stripped galaxies. This is basically, sorry, I took a picture of this. This is found by Giorgio Peluso that tells you that the fraction of AGN, even at fixed halo mass, depends on whether or not they are run pressure stripped or not, and so in maximizing run pressure stripped galaxies. And this is a plot shown by Luca Cortese that highlight the fact that even when there is little gas left, galaxies are still capable of producing outflow, perhaps because they have a recent burst in their star formation history. But what we don't fully understand, I think, is of course the redshift evolution. We spend a lot of time discussing this today, so since I'm running a bit out of time, I'm not going to comment on all this, and I'm going to leave you with this that tells you that we should understand what are the relevant environmental mechanisms responsible for building up the cluster population as a function of redshift. So how do you move from this to this is not fully clear. We have discussed it quite a bit. Since I have 2 minutes, unfortunately, I have to skip the important role of filaments. I'm going to summarize this saying that I believe these are new things to me. I believe they are extremely important to study because the universe is made of them, and the preliminary results suggest that the impact of filaments on galaxy evolution is perhaps minor, but we need larger surveys and deeper data, and I believe that LaDuma perhaps can help in this direction. Last thing that I want to say is about the metallicity. Funks shown this beautiful metallicity map where now you have thousands of H2 regions per galaxy, and you're not forced anymore to follow the trend of metallicity with radius, but you can really study how the metallicity varies across spiral arm of galaxies and aside with the metallicity trend, and this allows you to compare, to infer the mixing between the different phases. And now we have direct measurement of metallicity, a very, very high redshift, thanks to JWST, thanks to this Cecilia program that has been highlighted by Noah Rogers. However, perhaps this is the last point that I want to make, is that we may not be completely sure how metallicity are measured. So this is the talk made by Alessandro Marconi, show this home run method, where you rather than assigning, using a single phase metallicity measurement, you start to sample your log U, log NH plane in order to reproduce all the line profile that you have in your measurements. And you can come up with metallicity values that are different by a factor of 3 with respect to what you've been measuring before. So this can be degenerate. You need a lot of auroral lines and normal lines in order to do this kind of modeling, this kind of measurement. But since it appears that there is a discrepancy between the previous measurement and the new one, I think these new approaches need to be taken into account. So I'm running out of time and not gonna tell anything more about what we said. I'm just gonna say thank you for attending this conference. I don't know if this picture has been taken by astronomers, but if it was an astronomer, should be really, really interested in the environment, because most of the picture is occupied by what's not us, and must be also an high redshift astronomer, because if you zoom in, we have barely resolved. Yeah, thanks. Oops.
You broke the tradition, Antonino. I'm sorry.
Which tradition?
Talks was not bad at all.
Okay, so you left me without anything. Okay, let's see if I... No. Yeah, HDMI, sorry. Just a couple of minutes to wrap it up. Oh my. Really a few minutes. First of all, I want to say thanks to all of you for being here and for all the great contributions. I already spoiled it. Sorry. Wait, I have to... Yes, it's coming. Yeah, thanks. So thanks for all the fantastic talks, posters, panel discussions, questions, conversations, and everything. And in particular, let me give a special thanks to Antonino, who really had a very hard job. So I think we should give him a big applause. Yes. Let me also thank first of all, sorry, I have some stuff here that shouldn't be there. Let me go out and in. Sorry about this. This is in the way. Yeah. Yes, so I'd like to thank the scientific organizing committee. Some of them were here, and also they gave a contribution here for putting together such a great program. And of course, the local organizing committee, who has done a lot of work. You know, on the left, the official local organizing committee, who has done a lot of work, really, and everything, you know, all the emails that you received, and people that answered you, the web page, everything. It's on this side, but also on that side, I really would like to thank also local organizing committee with Alessia, Benedetta, Marco, and of course the people that brought around the microphones, so big applause. And the other thing I wanted to say, and you're welcome, because I think you also want to thank me, so... Thank you. It has been a pleasure, really. I had so much fun, you know. As Captain America says, I could do this all day. Anyway, a few more things. Do not forget to upload your presentation on this drive, and there you have the same. In the same directory, there is a subdirectory now called Photos, where you can find the official picture of the conference, and in the next few hours, days, you will find a lot more pictures that I took throughout the week. And please feel free to upload your pictures if you had some beautiful ones. I saw Yarle with the camera. Anyway, feel free. The video recordings of the whole conference will be put online, but please be patient, it just will take a few extra days. So yeah, this is one of the, and no, it was not taken by an astronomer, but I will tell you now who took. So this is one of the pictures, and there are some zoomed in versions, so maybe you will see yourself, you know, if you zoom in, but then you don't see the square anymore. Special thanks I have to give really to the OPA, the Opera Primaziale Pisana, and particularly Andrea Cinacchi and all the staff, which is, you know, it's this place. They gave us the room and, you know, the possibility to be here, and also the bistro of the opera with Valeria Vannucchi, the food, all the lunches and things. And I would like to thank our technician, Andrea, who stays with us all the talks. It must have been painstaking, really patient. And he's also the one that took the official picture from the wall. So Andrea, grazie mille, ma l'hai capito, grazie per tutto. Of course, I have to remember that it wouldn't have been possible to keep the registration fee so low if it was not funded by the RC program GASP. So yes, a big thank also to that, and of course the Comune di Pisa, who's not officially but in somehow sponsored. The last thing is, remember, tonight we can all be with Silvio at 8:15 p.m. You can enter at the Gipsoteca at Piazza San Paolo all'Orto. This is one of the things, so you have the opportunity, even if you don't want to stay for the conference, which is in Italian, I remind you, but you have the opportunity to visit the Gipsoteca di Arte Antica. And this is how you get there. So from here, you just go to Piazza dei Cavalieri, which by now you should all know, and essentially you go straight, you hit the Piazza San Paolo. It's really 10 minutes from here, so maybe see you all there tonight, and that's it. Thank you very much.
Sorry, you need to listen even though you don't want to. And I'm sorry I'm reading because I don't know if I managed to say it. So don't start right. So the RC is over, we said it many times, and we are really reaching a milestone, but GASP is not over. We really hope that our collaboration will be long-lasting, no? Sorry, no. And because we have so many challenges ahead, we have so many things that we want to do together as a team. This is really the good moment to stop and thank you. Thank you for everything, because you're an amazing person and you're an amazing leader. I really think that I'm talking about the entire GASP team. We are really honored to be part of your team. You really deserve a huge thanks for all this year. These 5 years has been incredible. We really grew from a very small groups, and now we are 50 people, more or less, that are involved. And you really kept us united every day along this huge and long trip. You always found some time for each of us. You managed to keep us together, especially in the hard times of the pandemic. We really started in the pandemic. At the beginning, we were really a small groups, and we were meeting in person, and we were just all squeezed in your office. But then suddenly, we couldn't have this meeting in person anymore, and you had to run 10 online meetings a week because we couldn't meet in person. You really taught us countless things. This is not the place to celebrate your scientific contribution, but we really want to celebrate your role in our lives. You taught us that with a smile on a face, patience, respect, but also with perseverance and determination, we can reach all of our goals and go anywhere. Really, thank you.
Just to say, I'm not retiring. So this is just the GASP end, but I'm not retired. So see you soon. See you. Thank you very much. And please take out the last posters because they need to